The beauty of studying field geology, in particularly a low metamorphic grade environment where rocks are deformed, but at the same time the initial structures, particularly when the sedimentation was happening, if those structures are preserved, these provide you a lot of added information. The most important information that we get out of this kind of features is the Younging direction, and that tells you that where you are on the stratigraphy, the beds or the layers you are studying, which are older and which are younger. If you get at least one and also confirm that the bed you are looking at is not overturned, then this is one of the beautiful findings in the field, because it tells you the Younging direction. So now we are going to see some of such features which actually can tell you that which is the Younging direction in the field. We see here such features that actually can give you the Younging direction. You can certainly imagine or certainly can figure out that these are the traces of S0, the bedding planes. Now, if we look at this particular area or this particular segment, then we see some features are here like this. Okay. And if I try to sketch them, I start from there. It's a very rough sketch I am trying to do. Sketching is one of the very important tasks in structural geology, because if you don't understand any feature in the field, it is important that you start sketching, and the necessary features that you would like to see, then it comes very easily to you, and you see them very nicely and can interpret them the way you want. So as you can see, it is something like that, and we see very clearly that this one, particularly this one, which I try to represent it with this, it has single feature, but the other one, this one, which I try to copy this one, it has multiple features inside it. Now, these things do form during the sedimentation process or before the lithification of the sedimentary rock, when the rock has a significant amount of water in it. So what happens? You have sedimentary layers of alternate, say, sand and other minerals or heavy minerals, and this is not lithified, and then if you have a shake, say a little tremor, then because you have a lot of water, these things try to sag, and they form in 3 dimension kind of a picture, something like that. So eventually these things you can consider as some spherical objects. If you cut them along this side, we are looking at the profile section, but if you cut them along the bedding plane, which is particularly in this section, you actually can see an elliptical section here, right. So if you can cut this side as well, then you probably would see this elliptical section, and that tells you that this was initially, when it formed, it was spherical. This particular structure is known as convolute structure. And this one, where you have only one convolution, this is known as simple convolute, and this one where you have multiple convolution within a large convolute, this is known as complex convolute. And all kind of features that form during the sedimentary rock formation with little tremor, these are together known as, it's a pretty long name, penny contemporaneous structures, or simply we call them seismites. Okay. Now, what is important here, if I try to show these in the sketches, you can clearly figure out that these things were deposited and then tremor happened, they form this sag, and that in a way convincingly tells you that because these are gravity driven features, so this is the bottom of the sequence, and towards this is the top of the sedimentary sequence. Therefore, here I see that this probably was the initial layer, and then it sagged downwards, which I can come here and mark it as the initial layer orientation, and then I see which way the convolutions had formed, and that clearly tells me that Younging direction of this sequence is towards this. So, in this case I know that this part has not been, or it did not undergo any kind of overturned folding. So, therefore, this sequence is giving you an Younging direction towards this side, or for this particular area this is towards the southern side. So, now you see everywhere, in wherever you particularly focus in this area, you will see this kind of syn sedimentary structures, and they always give you a direction of Younging. And this is apparently simple, though I marked this as a complex one, but sometimes they formed very densely and then they further deform, and then their deformation, if that happens in multiple times, then it gives a very complex structure. But if you are intelligent enough, can make nice sketches out of the features, you can figure out which was the Younging direction, or which is the Younging direction of the sequence you are studying in your field area. So, I showed you a pretty simple one, but these features could be as complex as this. Here what you see is convolute structures. So, as you can see, again the traces of the overall bedding are going like that. In this surface it is going like that. By the way, this is horizontal surface and this is subvertical. So, we are almost looking at the junction of horizontal and subvertical section. The north is in this direction, where the cap is pointing. You see here very clearly that some fold like features here going like that, but I tell you these are not folds, these are deformed convolutes. So, again let me explain you how it is. So, this is the top layer, and from there these convolutes sagged down and produced the seismite due to some tremors before the lithification of the sedimentary rocks, and these are all simple convolutes. So, if I try to sketch it, you can see that I start from here. So, it is going like that. I will try to catch these three only. The coin is somewhere here, and then the first one I see going like that. The second one is like this, and the third one is like that. And of course, you have internal laminations inside. I might have to add a little more asymmetry to this, and then this one, it has a thick layer here and then going like this. Now, theoretically, when these layers or these convolutes have formed, you can understand that they should form like this. In a very similar way, the way convolutes form or load balls form, but the difference between convolutes and load balls is essentially on the fact that convolutes are generally bigger in structure, bigger in volume, and at the same time it contains internal laminations. Now, these features that we see here, we see that they are not symmetric. That means this side and this side are not similar, but they are all asymmetric if I try to point the axis. And this is again happened because of the deformation, and to be very specific in this case, because of shearing. So, if this is the axis right now, it was initially like that, perpendicular to the trace of the primary bedding. So, it was like this initially, which I imagine to be the perpendicular of the bedding, and now it is like this. So, if you measure this angle, that is the magnitude of shear angle. Okay. So, from this angle you can calculate the shear strain of this area. So, there are lot of such features, and you can see that they are not all equal, and they are not equal because they have sometimes internally rotated or because of some other asymmetries and disturbances, and therefore, it is important that you take more data as much as you can other than the sedimentary features, also telling you the Younging direction. These deformation can give you an estimate of the magnitude of shearing in this region. Here we see one more important sedimentary structure or sedimentary deformation feature. You see here again, these are the traces of S0, and here you actually can see a tiny plane is exposed, that is your S0 plane, and this is confined with this folded S0, asymmetrically folded S0, and we will come to that part later. But what I request you to focus on, to look at this ball or ellipse like features here, 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 and so on. These are known as load balls, and they are also very important in defining the Younging direction. Again, if you try to sketch it here, I try to do that. So, here you have the coin somewhere here, let's do the coin here, and then you have the sedimentary layers going like this. You do not have to be an artist to do that, but just try to catch the necessary information when you are trying to do this practice. Something like that. And if you notice that these balls or these are sand rich. So, what happens eventually? Initially they deposit, so this is a sand rich layer, for example, and then if there is some little shake when these layers are in their pre-lithified stage and contain a lot of water, then with this shake what happens, these things, heavy things, try to sink in and form something like that, and sometimes they become even isolated and remain like balls in the system, and these are known as load balls. So, if you see them attaching with this, then you can clearly tell that this is Yanging direction. And these are also important strain markers, because you can imagine that when they sink in, they actually in 3 dimension are somehow spherical, or statistically you can consider them spherical, and if they deform, then they can take the shape of an ellipse in cross section or ellipsoid in 3 dimension if you have a chance to look at it in 3 different surfaces. So, clearly you can imagine that this area, for example here, it was initially a sphere probably, or a circle in this section, and then because of deformation it got stretched in this direction. And this is also evident from the lower bed, which is giving you the fold, right. You can see that this layer below is asymmetrically folded, and this tells you that it got the axial planar cleavage pretty much well oriented, similarly oriented with this ellipse. So, if you see it, it is this way, and here it is this way. So, clearly a shearing went on, and therefore you are seeing these load balls are deformed. At least if you can identify this section, I am not going to tell you which section is this right now, this will come later, but eventually if you can measure the long axis and short axis of these load balls which are exposed in this section significantly, you can give an estimation of the strain of this region. We see more load balls here, and just after the demonstration that I have given you a while ago, I believe you can figure it out. So, look at this for 2-3 seconds, I give a pause, and then I will show you where these load balls are, and I am sure you have already figured it out where it is, and just confirm by yourself that you have observed it rightly. So, these are the load balls we are looking at in this section, okay. And essentially you can see they are not spherical or circular in this section anymore. So, you see that these are the traces of the bedding, and again this bedding is folded asymmetrically, you can see it here. You can see the bedding is also folded asymmetrically here, and the initially spherical or circular load balls in this section got stretched and deformed. So, let me sketch it again, because it is always an important and useful practice to do it in the field. So, I will try to sketch this area only. So, here is the coin for your scale, and then you see this layer is going on, and you have a fold here and some other tiny folds going on here. And then you have a little cut here, which is not that important, and then some other layers are going here like that. And here, just right below this tiny hinge here, you have the first load ball that you can think of. Then you have another one here, and then you have the third one. The other layers are going like this way. You can see also one more layer is coming in this form and is getting folded, and then here you might be confused because you do not see what is happening, and so is happening with me. So, I can put some dotted lines, and then I can trace the layer here as well. But whatever it is very clear that it got folded here. You may also see some internal structures here. So, that can be a layer here like this, but nonetheless this load balls, you can certainly say that these are not circular in this section. So, stratigraphic top direction is this one, you can essentially tell, and if you measure the long axis and short axis of each and every load ball in this region, you can estimate the strain here in this region.
We are now standing near Dhalbhumgarh on the Chaibasha formation, and to my back along this direction is north, along this direction is east, and along this direction is west. So, this is a part of an abandoned airport, and there are beautiful thin sedimentary structures exposed on this platform over here. Now, the interesting point is there are lot of complex thin sedimentary deformation structures like convolutes and other structures like dish and pillar and so on. We have already demonstrated how these type of sedimentary structures, thin sedimentary structures form, and you know that they are mostly formed because of some external tremor or external shaking that disrupts the equilibrium between the sediment water interface, and after that, due to the fluid mobilization, or in other sense I can say that due to the escaping of water or dewatering, these kind of structures are formed. Now, as you can see, there are several structures. Say for example, here it is a beautiful dish structure, and these dish structures have been exposed here in very good fashion, and there are gradings between these dish and pillar structures. And the interesting point is that all these structures are concave in shape, and the direction along which these structures are concave points the Yonging direction. And similarly we can see that here is also an interesting dish type structure, and it shows a very beautiful concave surface. So pointing the pen along this concave surface, we can actually determine the Yonging direction of this sedimentary bed. Now as you can see, if I point these Yonging directions here and here and here, all these will give you some sense of rotation. That means the Yonging directions are not uniform, which tells us that this entire region is extremely deformed due to latter stage tectonic events. So that is why you are not getting uniform Yonging directions. So here it is an interesting exposure. You can see there are multiple dish type structures all around, randomly oriented within this tiny little exposure. So this gives you an idea how complex the sedimentary processes were at that time, and also the deformation events that came consecutively after the deposition of these sediments. Now there are interesting features like gradings within these beddings and laminations within these dish type structures, and from that you can estimate the Yonging direction from the concave side surfaces. These kind of structures generally form during some penny-contemporaneous shaking within the sedimentary basin, and the main process behind the formation of these structures is generally some sort of complex instabilities that are acting between the sediment and water interface. Now the water present within the interstitial spaces of these sediments, of these rich mud layers and sands, so those waters basically escape from that pore spaces or interstitial spaces during the external tremor, creating the sagging or the downward movement of these entire mass of sediment deposits, and they form these circular or dish like elliptical structures. From these structures we can estimate the Yonging direction, but as I said earlier, due to the extensive deformation of this region, the tectonic deformation has caused the rotation of these dish and pillar structures. That is why you are getting a randomized orientation of all these sedimentary deformation structures. So throughout this entire area, in this entire exposure, you will get multiple such complex surfaces, complex deformation structures, and from that we can actually interpret how these four regions are formed, and during the formation or during the deposition of the sediments, what kind of external activities took place that triggered the formation of these kind of seismite structures.
Sometimes it is important to find the bedding planes in proper way, because as I said that cross beddings and other things, they can be very deceptive and can misguide you in figuring out. Okay, so here it is. So what we see here, you can see, right, a number of bands are going along this direction, and you see the continuity of these bands also on the surface. And as we have repeatedly mentioning in this course, that to identify bedding planes you need to look for thickness variation, compositional variation, and sometimes some sedimentary features. Now what we see in the surface, there is no such sedimentary features other than bedding planes itself. So these are very much convincing ways to describe that these are the traces of the bedding planes, though you are not seeing the bedding planes exposed here properly. So, if you find an exposure where you do not have bedding planes, the bedding planes are not exposed, but you can see the traces of the bedding planes at different sections, which are just some fracture planes or erosional surfaces and might not have any significant, I would say, geometric interpretations that you do not use with them, but the traces of the planes on those surfaces are very important to determine the orientation of the planes. For example, here one can take the measurement of the lineation of these traces on this surface and also on this surface and also on this surface. While doing that, make sure that the two surfaces you are selecting for measuring the lineation data, their own strike and dip are not very similar. Otherwise, in StereoNet they will come closer and fitting them through a line would be a little difficult. So, again I have measured this orientation here, this orientation here, this orientation here. So, 3 different orientations I can measure, lineation orientation, and you can see the data of this one right now on the screen, this one right now on the screen, and this one also right now on the screen. You see these 3 data, and then we have plotted them on the StereoNet, 3 lineation data as 3 distinct points, and based on that we can figure out that what is the orientation of the bedding plane. And most importantly, because we have seen that in this place we also have bedding planes exposed, so we can actually match them if our method of measuring the planar data from linear data of their traces are matching each other or not. So, this is how you take different data sets from different planes, and together with all these things you can figure out that what is the actual orientation, and then you can verify them again. So, the importance of clubbing the data, working with them together is very, very important here. And speaking of togetherness, we use very good life of Ajit and Onu. So, they have marked their name here on this exposure. We have some fractures here. So, these are mode 1 fractures and some late intrusion of quartz veins throughout this rock sequence. We see it is there, and we will see more of these sedimentary features in different other sections in this area. So, we see here a quartz vein, as you can see here it is going like that, and we also see one little one here. Now, this is a plane, this is a fracture plane, and we do not have any good plane exposed to measure the orientation of the plane. What I mean that there is no direct way that I can measure the dip and strike of this fracture plane. How to do that? And we are going to learn this. So, we know the theory behind this practice is that if we have 2 lines, we can pass a plane through that. And in StereoNet, because we will be using StereoNet to demonstrate that, so in StereoNet the lines would come as 2 points, and then we can pass a line through these 2 points, and in StereoNet a line is a plane. So, if we can measure the lineation, that means the trend and plunge of this, which is exposed on this surface, we can measure the trend of plunge of this. You plot these 2 data on the StereoNet, and then you pass a grid circle, fitting grid circle through these 2 points, and the orientation of the grid circle that you can measure from the StereoNet will give you the orientation of the fracture plane. And to make it more convenient, you can also measure the orientation, the trend and plunge of this fracture on this plane. So, eventually you will have three data. So, I have measured the 3 data, this one, and this one. You can see values of these 3 data, the trend and plunge values on the screen, and then you can also see that what is the orientation of this fracture plane. So, with this I end my lecture. This is the end of lecture 6, and what we are going to learn in the next lecture, again we will divide it in 2 lectures, lecture 7 and lecture 8, where we will mostly focus on secondary structures. Thank you very much.